So we're returning to our linear programming, and I think the plan is this. I figured out what was the problem with Cplex. This is sadly, well, it took me a while to dig around, but I found in Stack Overflow actually technically they support only 3.6 and 3.7 Python, right? And we are only on 3.13 and 3.12, of course, right? So there are ways to downgrade, of course, install the older version, right? It's kind of pain, or you could also play around with the source code, and you can change your version, you know. But that's kind of hacky, which is okay, but it's a workaround. So what I'll do is we'll go through the theory, and then I'll see about using some alternative libraries, because it's not the only library. It's very pleasant to use, but it appears the IBM is kind of, well, it's active still, right? But it's not on GitHub, it's actually on IBM, right? Homepage IBM, and if you go to our homepage, looks like it's gone, right? So not very promising. There's some people who are maintaining. Maybe we should ask this guy, what's the story with the IBM? Maybe they're not paying them anymore. I don't know. But so kind of like semi abandoned it. But doesn't mean it doesn't work. It's just maybe it's a little too much. Nobody has taken time to test against newer versions of Python. All right, but we'll look something through SciPy or something like that. We can use that. Okay, let's go to our main where we left off at the outline. Do we have outline? Yes, linear programming, linear constraints. We know the continuous variables, right? Symbolic representation. Again, so this is very formal, right? In general sense, we minimize something or maximize, right? So again, remind that it has to be linear, right? And it has to be less or equal. It could be also equality, right? But you cannot be less stricter less or strictly more. So we go to this part here, right? And we saw this picture. Let's close this one. Yeah, we didn't download the library. The library kind of stuck. Basically, we know the solution already, right? So the way to solve it is basically one of the ways of solving it, as George Danzig found out, is, well, he figured this out, right? You can basically move along the edges and also the cross points where the actual solution must lie necessarily, right? So let's look at this again. The story is that, okay, we solved it, right? Unfortunately, can't. This library doesn't work right now. But so multiple. I was talking about this, right? So it's possible that you have multiple solutions if your function happens to, but you're trying to optimize, right? Happens to fit nicely with the same slope, right? Same tangent, right? As one of the limiting functions, one of the constraint functions, right? Then, of course, you have basically infinite solutions from A to B. Any of combinations of cell and desk here would work, right? You can use any of those basically, right? So again, that still works because it's still within the edge, basically within the cross points, right? This will give you the solution. So let's see. Maybe they didn't give an example, right? So all the points are same objective value, right? You always get this, whatever value it is, right? So, right, constant is binding. If the constraint becomes equality when the solution value is substituted, right? So graphically binding the constraints exactly on the line, right? This is here, right? Yeah. So desk at least 100 is not binding because the left and right stands are not equal, right? Yeah, at least 100, right? So of course it's possible. When you say infeasible, right? Feasibility analysis, is this thing actually possible, right? Can we build a spaceship to Mars, right? Can we build a infinite, energy engine or something? Or can we build a nuclear station in our backyard, right? You do a feasibility analysis. This real thing was going to work, right? So yeah, so here too. So infeasibility means there's no solution, right? We have all these too many constraints, and it's completely possible, right? We can't do. So here's an example. You say you need to make at least 1100 cell phones, right? Unfortunately, And also, how many desk phones? Also, like I guess 1100 or more, right? And of course, obviously, you don't have enough hours, right? These two functions, these hour functions, you just can't do it, right? There's no solution because these two functions, right? These two lines, basically fixed line functions, right? It's like you say, you come to your, to your manager, to your owner of the company, and say, okay, this is not, Alice, this is not gonna work, right? And Bob says, no, it might work, I don't know. So, but yeah, so you see why this doesn't work, right? Obviously, right? But again, this is obvious to see if you have two variables, right? If you try to maximize like five different variables, right? You're also dealing with, I don't know what else you'd be making pagers, I don't know, or what else could you be making, I don't know, drones and so on, right? Then of course, this is not visualized, it's hard to visualize that, right? So, okay, so infeasible, if you have, again, this dogplex here, this is, will give you this infeasible, right? To how to correct, well, you say, okay, this is not going to work, you basically say, okay, maybe somebody just had a fat finger and, typed in 1100 instead of 110, right? It was not realistic, right? So, but in feasibility analysis, right, it gets complex, so basically smart systems, smart libraries will tell you the answer is you have to relax, right? And by the way, relaxing, we'll see, this applies to more other algorithmic problems. Sometimes relaxing is a really good approach to solving something. The first step, you say, okay, this does not work. We have no easy way of solving it, but how about if you relax one of the constraints, one of the conditions of the problem, we can solve this. Maybe you have some really greedy approach or something, right? We can solve it, and then we can use that knowledge from solving the easy problem to use something for solving the harder problem, right? So this is one of the things, relaxing, right? So we change it, relaxation doesn't mean going to sleep or sitting on a beach, right? But this means you change some constraint, basically. It's extremely commonly used, right? So you say, okay, we let this in real life. You say, okay, those poor workers don't have to work more. Instead of 400, they have to work 440, right? So relax. Again, this does not only apply to linear programming in general. This sort of technique, right? So obviously you're solving a different problem, right? You're not collecting apples, you're collecting oranges, so to say, but it still can give you some useful insights, right? So maybe also, of course, you say, okay, so soft constraint, this constraint can be violated, right? Hard constraint, of course, is you cannot do any, that's it. This is a hard rule, right? So we had hard. So we can do this soft constraints. Let's do this. Yeah, we can add overtime, basically, right? So overtime less than 40, right? So that's like, maybe it'll give you some overtime, right? So there's a penalty, basically. It's overtime, right? Costs extra, you have to pay extra, right? So you can modify this. This is kind of nice. Docplex, of course, I don't think the SciPy, which we're using, does not support these soft constraints, right? So this is pretty cool, right? Really cool library, but unfortunately, like I said, it's not very well. Can we do maybe older version of Pi? I could do a different version of install Python. Older version here. Do we have? We can install older version. So component variable versus component model, right? So component variable is you can go, infinite in both, in at least one direction, positive or negative, right? A model is the objective value can be increased, or decreased without limit. Yeah. Again, this does not mean that it's the variables being unbounded does not mean that the solution is completely unbounded, right? But unbounded model is almost certainly not correctly formulated because basically you can basically get anything out of the model, right? So unbounded feasible reason, right? So if we, for example, say there's no constraints on assembly and painting time, right? Then this is kind of stupid. Basically, say okay, make infinite phones, cell phones. There's no answer basically, right? Because you keep going up because there's no limit on the time spent. This means you have infinite factory, right? Paperclip factory with infinite resource, whole universe basically, right? It's basically a useless model, right? Again, or models are kind of wrong, but this would be a really useless model. This would not be a useful model, right? So, okay, what else? So algorithms, right? So that this is actually how to use it. There are different ones, right? So simplex, right? George Danzig, right? So this is like the actual basis, right? It's an iterative method, meaning looping, right? You start with something possible and see if you can improve, right? You basically keep trying to improve until the function cannot be improved, right? So let's see how it works. So basically you start somewhere, usually the minimum, right? And you keep moving along the edges, basically, right? You vertex, vertex, vertex. At some point, you know one of the vertices, right? One of them will have the answer. Maybe two vertices will have, right? Possibly, but at least one will have. So basically all you have to do is find all the vertices, right? And then just move around, loop it through, right? All the vertices. And here, of course, it's easy. Of course, again, it means you have to solve these linear solutions, of course. But again, we know how to solve it. Again, when you take your linear algebra, it's relatively, straightforward, right? So you keep moving, basically, right? In two directions, right? Which direction first? Well, we can adjust this, right? Which maybe have some guideposts, which is more likely, but eventually you are guaranteed to either find the vertice which has the correct solution. If you find two vertices, it means there's probably the line, everything in between also works. Or if you go through iterate over all the vertices, right, and you don't find a solution which actually works at all, right? This means it's infeasible. The problem is not solvable at all, basically, right? So pretty simple algorithm, right? Just loop it. Let's just loop through. The only hard part is finding the vertices, basically, right? So pretty simple, but of course there are ways of doing it, right? So you go eventually, you loop through whichever way you go, eventually you'll find the solution here, right? Pretty cool, right? 300, 800, right? So there's some ways of efficiency. What do they do in 53? This is a good thing that they can do better. Because again, we're seeing this in a very simple example. You have only 4 equations, but you have like 100 linear equations, right? And maybe 50 variables, right? It's pretty hard to actually find all the vertices, right? So they made this revised simplex, right? Also dual idea of dual, basically, but the dual problem is something. You have a minimization problem, the dual will be a maximization problem, right, and vice versa. So in this case, maximize something, minimize something, same thing, basically, right? Dual, right, and so basically sometimes it might make sense to solve the reverse problem sometimes, right? That might help, right? So, vertex is basic solution, right? So yeah, what else do we need to know? I think that's basically it. These are all about dealing with simplex, which we don't know, doesn't work yet currently. So let's say, okay, yeah. Sometimes in the difficult problems, there might be sort of like I wouldn't say an infinite loop, but kind of like infinite loop. It's called degeneracy, degenerates, right? Meaning it's sort of like moving between start cycling between non-optimal solutions, right? So, but usually, of course, how do you solve this, right? You say, okay, well, you have some sort of counter, say, okay, you are looping, right? You have some ways of preventing this, right? So, what else? These are all technical details, barrier methods, right? Right, you can find optimum here. So, these are all good stuff, but now we'll do integer. That's something we'll solve next time. But for now, right, let's do markdown. No, not here. Control Z. Here, I'll do this here. Solving linear programming with SciPy. Right, this is a big library. SciPy is a big scientific programming language, scientific library in Python, right? Well maintained, unlike Cplex, right? All right, and works on current Python, right? So let's see if it's included. I think it is included. Now the question is, I think it's SciPy, right? Right. I think let's import it. Code. I think let's import optimize module from SciPy. Yeah, optimize. I think linear programming, or we can optimize as opt. Right. Yeah. Right. So something like this. As we're renaming using ls. So also opt is or alias, right? Right. Okay. And the problem is this is right. The documentation. The issue with SciPy, of course, it's one of the. It's so big. It's not as nice to use. Again, I have not really used often. So I remember that you had to make some sort of normal forms of this problem. I think you have to make them negative. Optimization problems, everything has to be minimized, so the constraints are kind of pain to set up. Let's take a look how it was, right? So our problem, let's try another objective. Let's define constraints for our objective function. Here we have to make them negative. Yeah, minimize. So it will be, C constraints, right, be negative 12, I think, negative 20. Let's see if this works, right? Right? So it's reverse. Essentially, you're doing minimizing, I believe, minus the function is like negative. So reverse. Yeah. Now we need the coefficients, right? On these, I think we can use as is, I believe. I believe we can use them as is. Let me see again if I can find out documentation for this. Let's see. I think we can do it like this. So coefficients, let's call them, I don't know. Or maybe objectives. I guess I'll call them objectives. Sorry, I'll call them objectives. Objectives, right? Objectives, right? Constraints. This will be better. Constraints. All right, and it will be a two-dimensional. Yeah, exactly. Those will be good. Now also we also have the bounds, right? And we also have bounds. Right? Yeah, those are bounds, right? So 100 none meaning none here. None means positive infinity here, right? Okay. So you see, this is not as nice to use because you have to basically look at the documentation, right? Or use some sort of ask ChatGPT and see if this works actually. Hopefully, right? So we have our constraints, right? So essentially we have when we get 490, we need to also enter the 490, I believe, somewhere, right? Yeah, and now we need to put the right side. And now we need the right side. Yeah, we need the right side, right? Right side. Yep, okay. Again, I'm trusting Copilot a little bit here. We'll see if this works. Maybe, okay, if we get different answers, then we know it doesn't work, right? Well, we have three choices. We have three possible outcomes. There will be a syntax error. Well, we'll get wrong answers, or, well, or we blow things up. No, but hopefully it will work and we get the right answer. Okay, so that looks okay to me. So far, if I remember correctly. Now let's solve it. I think that's it. Yeah. Result. Yeah. C is objectives. Yep. A constraints. B right side constraints. Bounds. Method simplex. Okay. Print results. Let's see. Print. Oh, come on. Yeah. X value. Right. Okay. Okay. Let's print them. Status. Alright, let's print the result. All right, that's it. Let's see. Okay, are we ready to go for it, or maybe we need something else, right? Let's see. Oh, it prints connected. Success? Wow, it worked. It worked actually. Amazing. Right. Okay. Except you get a nasty depreciation warning, meaning simplex is too old school, I guess, for SciPy. There's going to be a new version, so use one of the other ones, highs, new code. They are better solved because this is an old school solver. Again, we have a simple problem. So yeah, so we can solve. So we know the values if they are in scientific notation, and again the function. Again, since we are reversing the value, right? So that's the only problem, right? So this works, right? Print them one by one, right? So I'm pretty happy with this approach. Actually, surprise, right? But the problem is again. So SciPy. So let's print the results one by one. More fun, right? Values, right? We have two of them. We have two. We have two additional variables, right? And what else? Success, right? I hope success is true. Yes, we know this is of course. Yeah. So again, so notice again. So this means we have to reverse scientific maximum value, right? Because we are basically we're saying we want to minimize this function, right? Essentially, right? So conclusion. So markdown tips on using SciPy. Optimize. Well, first it would be nice to have help, to have some tips. So to use SciPy, we had to use to convert or maximize function to minimize function, essentially multiplying both sides of our optimized function by -1, right? So maximize again, not very user friendly, but it's I think it's doable, right? So if you do this again, well, the good news for you is of course I won't probably make you do this, right? And I probably won't make you also do this by hand, but please know roughly know what's happening, right? And you probably there are other libraries, there are alternatives, right? There are alternative libraries, yes. So let's do this. Let's do Python, and of course other language too. So we'll do code alternatives to Cplex and SciPy for linear. Yeah, I'll tell you. Pulp is the one. Yeah, Pulp is the one. There's also something else, right? Gurobi, but this I think is paid. Gurobi is paid. Gurobi commercial solver, so paid, right? Free solver, right? You could try again. Maybe it's some extra credit. You want to click and play around with something but go around with these. By the way, yeah, this possibility. So these would be this. I mentioned this maybe before, as far as grades go, right? If you are, for some reason, not something that you want to gain extra point, right? There will be a possibility to have a report on algorithms, right? So this one possibility would be just to work on find one of these libraries, how they work, right? So you would be welcome to write a report, notebook on using one of these libraries to get that extra credit point, right? All right, but not, of course, there are many other things you can do too, of course, right? And maybe you don't have to do anything, but yeah. So, all right, so this one I'll convert this to alternatives. Yeah, I'll convert this to Markdown. All right. Yeah. I'd like to make some links. We want some links actually. Let's see if we can get some links here. Link to SciPy. Okay, let's check the link if it works. Looks okay. Yeah. You see, yeah, that's how it looks, right? So this is, yeah, this is pretty good. So you can see how to do it, right? So you provide all these weird arrays, basically a bunch of lists, basically, right? You know, they make it very user-friendly, but it's not too hard to figure out what you need to do, right? So you minimize, only minimize. Now, okay. What else you want? Let's see here. SciPy, link to Docplex, link to Groovy, link to Guru. I don't know. Let's see if this is actually how much we have to pay for these guys. I wonder. I never use them. Groovy optimization. Pricing, solution. So yeah, if you're academic, it's free actually, right? But of course, as usual, right? It's everything, right? They probably want you to be a big company, pay them a lot of money, probably. Okay, so one thing, of course, is if you can't find out the price, that means it's really expensive, right? Let's see if we can find the price. So can we find the price? Academic for graduates, academics, burrito optimization game. Okay, what is that? Yeah, free educational. Okay, yeah, you need your Groovy account, of course, right? Power optimization, but I want to see what the price is. Center, register. I wonder. Yeah, this. I don't know, free trial, but free trial. That's. I can't even find the pricing. I don't know. That's not really good. Always free for academics, students. I don't know. Maybe you can figure out the price. I don't want to. But it sounds really suspicious, little sus on that. So, how about what else do we have? What other options we have? GLPK. Okay, so let's try that one. Link to GLPK. Let's see. This GNU, of course, is a big granddaddy of all the open source packages, right? So it's a set of routines written in C, right? Probably, I don't know, Stalin himself or somebody else has written them, right? Very old school, like from 2000. Looks like somebody actually from Moscow Aviation Institute wrote this actually, right? Looks like, but now of course it's free, so open source. Hopefully no backdoors, hopefully, right? But yeah. And what else do we have? I think there's one more package which suggestion. I had somewhere listed somewhere, something, other alternatives somewhere. Oh, there's something by Google apparently too. Yeah, Google or tools. Yeah, this is developers, and again, very knowing Google, right? Route, schedule, plan, assign, solve, right? Fast and portable solver for combinational optimization, right? Gold. But there's competition for this stuff, by the way. Yeah, this is serious business, actually, right? There's competition for this, right? So, for optimization, yeah. Commercial source, Groovy or Cplex, open source, SciPy, or Google Silop, or ours in CPC. Yeah, okay, right. Open source software, so sweet, right? So this is something to consider, another possibility. And finally, what else we have? I saw there's another more. Pulp, GLP, SciPy Omo. Okay. Okay, how about PyOmo? Into PyOmo. Yeah, okay, let's see if this works. It looks promising, stable. So no hallucinations so far. Very good, very good. Right. But I think also most of these things, some of them offer ability to work with other packages. Again, but this of course is just technical craft you have to go through. So links to reference to. Okay, and I will make this. NumPy we don't need. SciPy we needed SciPy, and I think we are done. So. Okay, now convert to Markdown. Okay, good, and I will save this. Update the documentation. Added SciPy example. links to documentation, or links to alternatives. Okay. So now we have a couple minutes. So next week, I have not completely decided yet what we're going to do exactly. This is our algorithms, right? So I'll need to rearrange. The plan is for most of the rest of the semester we'll mostly be working with graphs, right? So that's the plan. I'm not sure if we're going to start on a Tuesday or possibly on Thursday. Maybe we'll do one more lecture on optimization or something. But we'll basically be dealing with graphs, right? So there's lots of algorithms to explore. Maybe we'll do also some string algorithms, maybe. But yeah. All right. Any questions? Anything on linear programming? Idea? I hope we got the idea what it is, right? Why would you want this actually, right? So anytime you can have some sort of write out the problem with linear equations, well, then you can use linear programming, right? No. Okay. So thank you everyone. I'll see you guys on Tuesday.